In this segment, I want to start talking about Chapter 11. In Chapter 10, we talked about energy and the conservation of energy. And so, the conservation of energy told us that the total amount of energy remains constant through any process in a closed system, right? So any process in a closed system, the total amount of energy remains the same. Chapter 11 is all about energy usage. In the last chapter, I had mentioned that energy is only useful to us humans when it transforms from one form into another. And when that happens, the total amount of energy that we start with is always exactly the same as the total amount of energy that we end up with. So except for a very few specific situations that we'll talk about, called reversible processes, anytime energy transforms from one form into another, yes, we get some useful energy out, but we also always create some thermal energy. So then that thermal energy is just not very useful to us humans. So again, in any process, in a closed system, the total amount of energy we start with is equal to the total amount of energy we end up with. However, we may not end up with as much useful energy as we started with. So let's look at some processes to see how that works. Here we see some energy transformations. Let's kind of describe what's happening in each of these three situations here. In this case, we see sunlight striking the solar cell. So light energy comes in and it gets stored in a battery, and then later at night, that light energy is released. Okay, so light in and light out. Here we see light energy is absorbed by these soybeans, and miraculously, these soybeans are able to convert that sunlight energy into chemical energy stored in molecules that are in these plants. And then we can process those soybeans, create a little bit of wax, stick a wick in it, make a candle, and get light energy back out. Light energy in, light energy back out. Kinetic energy of moving air makes these wind turbine blades turn. The turning turbine blades turn in a generator, which creates electrical energy, which can make blades of a fan turn. Here we start with kinetic energy of moving air. What do we end up with? Kinetic energy of moving air. So, in each of these processes, we end up with exactly the same kind of energy out as we ended up in. How do the amounts compare? How does the amount of light energy we get out here compared to the amount of light energy the solar cell had to absorb in order to make it happen? How does the amount of light energy I get out of this candle compare to the amount of light energy these plants had to absorb in order to make it happen? How does the kinetic energy of the air that coming out of this fan compare to the kinetic energy that the wind turbine absorbed in order to make this happen? In each case, we get out a very small fraction of the energy that we put in. We only get a tiny fraction of the light energy out that was absorbed from the sun during the daytime. Well, conservation of energy tells us that the energy in must equal the total energy out. Well, what happened? Well, there was a lot of thermal energy created in every one of these processes. So, yes, we did something useful, but we also created some thermal energy. And that thermal energy is in a way special. It's special because we can never kind of recover it back, right? So that thermal energy is just not very useful to us anymore, right? So when I run this fan, my room is slightly warmer for having run my fan. But that's thermal energy, and so the conservation of energy still holds, right? But I cannot take that my room is slightly warmer energy, that thermal energy that's absorbed in my room, I can't do anything useful with that ever again, right? So to us humans, that energy is no longer useful. Yes, it still exists. Conservation of energy tells us that. But it's no longer as useful. To introduce a new term that we'll revisit at the end of the chapter, the entropy of that energy is much higher when it's thermal energy distributed throughout the room in an unuseful state than when it is, say, stored as electrical energy, or if it is, say, stored as chemical energy in some wax, or stored in a battery, right? That energy, when it's stored and available for use, has much lower entropy than when it's distributed evenly and is in the form of thermal energy. We'll come back to that idea of entropy later. For right now, let's put a little bit of mathematics on this idea of what efficiency is. So here's a situation. In some cases, power plants produce excess power that they are unable to sell right away, and so they might need to store it in order to sell it for later. One way to do this would be to store it as potential energy in some water that is elevated above the surroundings. So let's just say that a power plant, we are a power plant manager, and you've got an extra 100 joules that you need to store. Okay, well, we're going to store this 100 joules in the form of potential energy of this water. So we're going to have to pump this 100 joules uphill. Now, we're going to have to use an actual physical pump for this, right? And if you put your hand on that pump, it's going to get warm, right? So we're creating some thermal energy. So let's just say that it costs us 25 joules of thermal energy in order to get this 100 joules of water pumped up here. Well, so we had 100 joules to start with, but we didn't end up with we had 100 joules to start with, but we did not store 100 joules. We only stored 75 joules. Why? Because we created 25 joules of thermal energy. Okay, well now it's stored there. In order to sell it as electricity, I have to run it back through a generator. So now I've got to go send it back downhill and through the generator. And guess what? That generator gets warm as well. So that generator also produces 25 joules of thermal energy. So what did I get out? I got out 50 joules. So in this case, I got out 50 joules, but it took me 100 joules in order to get that 50 joules back out. And so this is the idea of efficiency. That 50 joules that you lost to thermal energy, it's gone. It can never be useful to humans again. It's very high entropy, and it's just not useful. You can't use it to run a generator. You can't use it to run your computer. Nothing like that. It's not useful. And so let's introduce the idea of efficiency with this equation. It's what you get over what you had to pay, which is a nice way to visualize this. We'll talk about a slightly different way to define it in just a second. So in this particular case then, what did we get? Well, the point of this whole process was to store that 50 joules. So what did we get? We got 50 joules of stored energy. What did we have to pay? Well, we had to put in 100 joules of energy in order to get out 50 joules. So what is my efficiency? It is 0.5 or 50%. That's the efficiency of this process. Okay, that's actually not too bad for, as we'll see, doing some specific examples going through this chapter. This is not bad for a real process. Another way to think about this efficiency here is we could also think about it as useful energy or power out divided by total energy or power in. It's the same as this business on the PowerPoint, the what you had to get over what you had to pay. Sometimes it can be a little bit hard to figure out what these two things are. So this is just another way of visualizing it, another way of wrapping your brain around it. Let's do a quick example. Light bulbs are rated by the power they consume, not the light they emit. So a 100-watt incandescent light bulb emits approximately 4 watts of visible light. What is the efficiency of the bulb? For those of you that may not know, an incandescent light bulb is the old-fashioned type of light bulb with a little coil of wire inside. And that coil of wire is very thin and it glows red hot. And that's what produces the light. So what's the efficiency of that type of bulb? And this is typical numbers. Well, here I've written our definition of efficiency. And in this case, since they've given us powers, I've written it as power. So this is useful power out divided by total power in. Well, what is our useful power out? What's the point of running our light bulb? It's that 4 watts, right? That's what we're hoping to get out of our light bulb, is some light. It's called a light bulb. And so what did we have to put in order to do that? Well, it was 100 watts in. Notice my watts cancel, and I end up with 0.04 or 4%. So that's a pretty abysmal efficiency. That means for every $1 that you spend on electricity running an incandescent light bulb, 96 cents of that dollar you spent heating your house up, and 4 cents you spent lighting your house up, which was presumably why you ran the light bulb in the first place. So it's pretty depressing, really. It's even more depressing when you figure that that 96 watts is unuseful to us, right? Humans can never get any use out of that again. All it does is heat our planet up. Okay, so 4% efficiency, that's pretty bad. This is why these more modern light bulb designs have become so popular. A CFL, compact fluorescent light, those can be about 20% efficient, much, much better. Still not that great. LED lights, or light-emitting diodes, they can have efficiencies, it varies depending on the color, pushing 40% though. The efficiency of an LED light bulb can be up to about 40%. And interestingly, the efficiency of the LEDs, that's limited by the atoms that make up the LED. It's limited by the atomic structure, by the electron energy level structure of the atoms that make up the LED in a very interesting way that we'll scratch the surface of next semester, hopefully, if we have time. Okay, notice also that this jives with our other definition of efficiency, what we get over what we had to pay for, right? So what we get is 4 watts of visible light, but we had to pay the power company for 100 watts of energy, of power. Technically, we pay the power company for our energy use, not our power consumption, right? So power is a rate, and the electric company sends us a bill at the end of the month for the total energy usage, or power times time. At any rate, what did we have to pay for? We're paying for the 100 watts. We're not paying for the 4 watts. So would we get 4 watts? Would we pay for 100 watts? Our efficiency is 4%.